All right, welcome everyone. Today, we're diving into the world of linear algebra. But we're not just going to learn some theory, we're going to solve some puzzles. We have two really elegant problems that seem completely unrelated on the surface. So, let's jump right in.
So, what is the link between independent polynomials and two matrices with a hidden connection? It sounds like a riddle, I know, but it all comes down to the power of pure logic. And you're about to see how the exact same set of tools can crack both of these puzzles wide open.
Okay, so our first puzzle is all about polynomials. Imagine you've got these two simple first-degree polynomials, right? And we know for a fact they're linearly independent. The big question is, what happens if we make them a little more complicated, say by adding a squared term? Do they stay independent? Let's find out.
Okay, before we go any further, let's get on the same page about this term linear independence. What does it mean? Well, it's actually pretty simple. It just means you can't get one polynomial by just, multiplying the other one by a number. They're just fundamentally different. You can kind of think of them as pointing in completely different directions. And that one idea, that's the key to this whole first puzzle. So how do we prove it? We're going to use one of my favorite tools in the mathematical toolkit, proof by contradiction. The strategy is, well, it's kind of sneaky. We're going to assume the opposite of what we want to prove is true. Then we'll just follow the logic and see where it takes us. And if we've done it right, it should lead us somewhere totally impossible. All right, let's get our hands dirty. First, we make our big contrary assumption that our more complicated polynomials, Q1 and Q2, are actually linearly dependent. So what does that mean? Well, by definition, it means one is just a multiple of the other. We can write Q2 of x is just some number, let's call it alpha, times Q1 of x. From there, we just expand it all out. And since these two polynomials are supposedly equal, every single one of their coefficients has to match up. That gives us this neat set of equations. So now we've got these three little equations. But here's the trick. We don't need all of them. The whole secret to cracking this puzzle is to just focus on two of them, the ones for the constant terms and the x terms. Why? Because those are the pieces of our original simple polynomials.
And this is where it all starts to click. If we just look at those two equations, a2 equals alpha a1 and b2 equals alpha b1, we can basically reconstruct a piece of our original polynomial. Look at that. a2 plus b2x is the same thing as alpha times the quantity a1 plus b1x.
What does this tell us? It's pretty unavoidable, really. It means that our original, simpler polynomial, p2 of x, must be equal to alpha times p1 of x. And, by definition, that means they are linearly dependent. And, hang on a second, contradiction. This is it. This is the moment where a whole argument flips on its head. The conclusion we just reached, it's a huge problem. Remember back at the very beginning, the one thing we were given as a fact? That P1 and P2 were linearly independent, but our assumption just led us to prove they're dependent. That's impossible. So our initial assumption has to be wrong. It's the only explanation, which means the opposite must be true. The more complex polynomials are indeed linearly independent. And just like that, puzzle number one is solved. All right, one puzzle down, one to go. And now we're moving on to what I think is the really fascinating part of this explainer, a puzzle with matrices. This one's got a few more layers to it, and it's just a fantastic showcase of how one tiny property can set off a whole chain reaction of logical consequences. Okay, but first we need the master key to this entire puzzle. It's the definition of similar matrices. Basically, two matrices, A and B, are called similar if you can turn A into B by doing this kind of matrix sandwich, using some invertible matrix M and its inverse. So B equals M inverse AM. This one equation right here is everything, so burn it into your brain for the next few minutes.
Okay, so here's the first part of our challenge. We're told that if you square matrix A, you get the identity matrix I. Simple enough. Our job is to prove that matrix B, which we know is similar to A, has to have the exact same property, that B squared also has to equal I.
So let's walk through the proof. It's actually really elegant. We start with our master key, B equals M inverse AM. Then we square both sides. Now look at what happens when we write it out. We can regroup the terms in the middle and you see this beautiful thing happen. M times M inverse, a matrix right next to its inverse. They cancel each other out and just become the identity matrix I. And since multiplying by I doesn't do anything, it's like they just disappear. This simplifies everything down to B squared equals M inverse A squared M. We already know A squared is I, so we plug that in. And would you look at that? B squared is I. Done. Okay,
That was the warm-up. Now for the really cool part. We get one more piece of information, just one. We're told that the equation ax equals x has only one solution, the trivial one, where x is just the zero vector. And with that tiny little clue, we have to prove something that seems kind of impossible. We have to prove that A and B aren't just similar, they are literally the same matrix. How on earth can we get there from here?
Well, first things first, let's take that clue and see what it's really telling us. We can move the x over to the other side, so we have ax minus x equals 0. Now here's a classic linear algebra move. You can always multiply a vector by the identity matrix without changing it. So we can rewrite that as ax minus ix equals 0. And why do that? Because now we can factor out the x, which leaves us with a minus ix equals 0. This is a much more useful form.
And that equation tells us something huge. There's a fundamental rule in linear algebra. If the only way a matrix times a vector can equal 0 is if the vector itself is 0, that means the matrix is invertible. It has an inverse. So that little clue just helped us uncover a hidden secret. The matrix A minus I is invertible.
Okay, check this out. This is where it gets good. On one hand, we have our original fact that a squared equals I. We can rearrange that to a squared minus I equals 0, and that factors out to a minus I times a plus I equals the 0 matrix. On the other hand, we just figured out that the first part of that, a minus I, has an inverse. It's time to put our two clues together. So, since we know a minus I has an inverse, we can use it like a weapon. Let's take that factored equation and multiply both sides by a minus I inverse. On the right side, well, 0 times anything is still 0, but on the left, that's where the action is. The inverse a minus I smacks into the original a minus I, and they cancel each other out completely. All we're left with is a plus I equals 0, and that can only mean one thing. A has to be the negative identity matrix. And now for the final piece of the puzzle, there's a special property of matrices like negative I, which are called scalar matrices. They are only similar to one thing, themselves. So if we know A is negative I, and we know A is similar to B, then B has no choice. B must also be negative I, which means A equals B, and that is how you solve puzzle number 2.
Okay, so let's take a step back for a second. We just tackled two puzzles that on the surface looked totally different, right? One was about polynomials, the other about matrices. But the way we solved them, that's where the real connection is.
It's all about using the same fundamental toolkit. Think about what we did. We started with crystal clear definitions. We used powerful strategies like proof by contradiction. We followed the logic step by step, no skipping ahead. And crucially, we took different facts and clues and mashed them together to find something new.
And that really is the whole point. Getting the right answer is great, sure. But the real beauty, the real power, is in the path you take to get there. It's that careful, logical process that doesn't just give you an answer, it gives you certainty.
You know, this way of thinking goes way beyond math. It's really the engine behind any kind of good problem solving. So I'll leave you with this question. What other big, messy problems out there, in science, in business, anywhere, are really just puzzles waiting for someone to apply these same simple, elegant tools? To start with what you know for sure, and just follow the logic, one careful step at a time. Thanks for digging into this with me.